time we looked at the comparison tests. This is theorems 2.6 and 2.7. This is on page 15. So the comparison tests were where you examined a given series by comparing it to a series which you know the status of, meaning that you know already whether the comparison series converges or diverges. And the comparison test worked by taking another series and making the appropriate comparison with that series with one of your known series. And we remarked, it's there in the middle of page 15, that we often use, or I think we almost always use, one of the hyperharmonic series as the comparison series, the series that you know about, okay? Because we've got a complete understanding of the convergence or divergence status of the hyperharmonic series. So that's the series where you add up all the terms 1 over m to some power p. And whether or not that converges or diverges just depends simply on the exponent p. It converges when p is strictly bigger than 1 and diverges when p is less than or equal to 1. And that borderline case between the convergence or divergence was when p equals 1, and that was our nice first, one of our initial examples of a series was the harmonic series, okay, which is, only just diverges in a sense. It's the borderline between convergence and divergence in this hyperharmonic family of series. The comparisons can be made in one of two ways, either by using an inequality and showing that the terms of your series are less than or bigger than the terms of the known series. It's a less than inequality for trying to prove convergence and a greater than inequality for trying to prove divergence. That's the kind of comparison you make. So we looked at that last time. Or an alternative way of performing the comparison is to do a limit comparison test. This is where, you look at the limit of the ratio of your series, the series you're examining, the terms from that, and the terms from the known series. So you look at one of those ratios there, either AM over CM, where CM are the terms from a convergent series, or AM over DM, where DM is the terms of a divergent series. And it basically says that if that limit has a value, if it is convergent, so if the ratio is tending to some limiting value, then that will mean the series you're looking at has the same behavior as the comparison series, okay? You can kind of think of that as saying that, well, in the long run, if you wait around long enough, the terms from the series you're examining are acting like some fixed multiple of the terms from the known series. So because one is just a rescaling of the other one in some sense, then if one of them converges, so will the other one, or if the comparison one diverges, so will the series you're examining. Okay, so that was a quick recap of what we looked at last time. So there's a few more tests to look at. We won't give formal proofs for them, but we'll give some motivation or a sketch of what the arguments would be for these. And then more importantly, we'll look at some examples, okay? So we'll discuss three of them now, and then look at some examples. So they are the alternating series test, the ratio test, and the root test, okay? Theorems 2.8 to 2.10. So if we look at theorem 2.8 first, which is the alternating series test. I'll just discuss each of the three tests first, and then we'll look at a collection of examples. Okay, so let's have a read of this. So this refers to alternating series. An alternating series is one where the terms are alternatively positive and negative, okay? So you have a positive term, a negative term, a positive term, a negative term. So if you think of what that says and notationally, that means the series can be written in this kind of form, where the AMs are all positive numbers, and then you have this alternating plus or minus sign. So if this minus 1 to the power m, so that would be where initially the first sign was a negative 1, or alternatively, It could be minus 1 to the power m plus 1 if the first term was to be positive and so on. But having this minus 1 to the power of either m or m plus 1 means that produces the alternating positive and negative sign, okay? Because a power of minus 1, an integer power of minus 1 is either going to be plus 1 or minus 1. Okay. So what does that say for the partial sums? So the partial sum sk, which is the sum from n equals 1 up to k of an alternating series, how to think of the behavior? Behaves as if it is stepping up and stepping down, if you like. Or stepping left and stepping right, depending on how you put the number line. So that could be stepping left and stepping right. So what I mean here is if you were to graph this, so if you have the index, so we're going to graph k, so this would be the index k. So k equals 1, k equals 2, 3, 4, 5, 6, 7. Well, the first term is going to be minus a1. So s1 is somewhere down here at the level minus a1. But then you're adding on the term a2. So s2 jumps up to take some value up there. But then the next term in the partial sum is going to be negative. So it's going to drop down a bit. S3. Then the next term will be positive. So it's going to jump up a bit. So because of the alternating positive and negative sign, the partial sum is jumping up and jumping down, jumping up and jumping down, because you're either adding on a negative term or a positive term. So the conclusions of the alternating series test, you can kind of understand them by thinking of this picture. When is this kind of process going to be converging? If you've got this infinite process, which is stepping up, stepping down by a certain amount, stepping up, stepping down, and you're taking a different step size each time, when is that process, or what feature does it have to have in order that it's going to approach a limiting value? Okay, so you're thinking of the sequence of partial sums, whether that has a limiting value, and that's the same as whether the sum of the infinite series has a limiting value. Okay. Well, if you look at the statement in the test, the key point is, and this is the, sorry, we need to make a correction here. I've got my inequality sign the wrong way around. So this in the notes here, I've said it in words, right? So this is the correct statement here. We need the terms am to be positive and decreasing. But the way I've written the inequality there, looks like the terms are increasing. So this inequality there, so you need to fix the statement. I'll correct it on the online copy afterwards. So fix the statement of theorem 2.8. That inequality should read that am plus 1 is less than am, or less than or equal to, strictly less than am. I think we need, it should be changed to strictly less than am. We need the terms to be positive and strictly decreasing. So that means you're stepping up and stepping down, but the step size, well, we need the step size to be converging to 0. So if the step size is decreasing, and if it's converging to 0, so if the limit of the am is equal to 0, where m is the step size, then we are stepping up and down stepping up and down with step size converging to 0. So it'll be some kind of picture like this, just sketched out figuratively, stepping up, stepping down, stepping up, stepping down. But if the step size is decreasing and converging to 0, you're going to see the partial sums tend to some limiting value L. Okay. So if that's the case, an alternating series will only converge if we have these conditions are true. If the step size is decreasing and converging to 0. If the step size isn't converging to 0, so if the limiting value, or if there is no limiting value for the step size, or if there's some non-zero limit, well, if there's a non-zero limit to the step size, then ultimately how the partial sums are going to be behaving is they're going to be stepping up and stepping down by that fixed amount, which is the limiting value of the step size. So the series won't converge because it'll settle down to a type of behavior which is stepping up by a bit, stepping down by a bit, stepping up and down by some fixed amount. So it's never going to settle down to a limiting value. It will always be hopping between two different values. Okay? But where the step size is converging to 0, you get this kind of zeroing in behavior in the partial sums, and the whole series will be convergent. Okay? So that's a little discussion of the alternating series test. The next test is very important and very, very powerful, and this is the ratio test. So let's look at the statement of it. So it's not a comparison test. You're not taking your series and comparing it to some other known series. You're just focusing on the series itself. So let's look at the statement of it here. We're considering a series of positive terms, and we're going to look at the ratio of consecutive terms. So we're going to form the ratio am plus 1 divided by am. So that's a general term in the series divided by the one that came before it, isn't it? Okay, that's a ratio of consecutive terms, and we're going to take the limit of that ratio. And it's the value of the limit which determines the outcome of the test, which determines the convergence status of the series. If the limit comes out as being, now because all the terms are positive, the limit will be non-negative, will be greater than or equal to 0, if this ratio is a convergent sequence. If this limit L comes out as strictly less than 1, then the conclusion is that the series, the sum of am, is a convergent series. If the limit comes out as strictly greater than 1, then you also get a definite outcome. The outcome is that the series is divergent. However, the one remaining case, if this limit comes out as exactly 1, then the test is inconclusive. Okay? It could be that the series you're looking at is convergent, or it could be divergent. You would need to look at other methods, maybe other convergence tests or other type of investigation of the series to determine whether it converges or not. Now, the main idea of the proof of this is if the limit of am plus 1 over am equals L, if this limit exists and is equal to L, so if this exists, then the main idea is eventually we have that am plus 1 will be approximately equal to L times am. Okay, because if the limit of the ratio is L, eventually, if you wait around long enough, the ratio am plus 1 over am gets very close to L. So just speaking roughly or approximately, am plus 1 will be approximately L times am. And so the series, the sum of AM, will be acting approximately like approximately like, it's two P's and approximately, isn't it? Two P's. Not sure. The series will be acting approximately like another type of series that we know about. What kind of series does this look like? Where one term in the series seems to be approximately some fixed multiple L. See, L is some fixed quantity here now. Some fixed multiple of the term that came before it. Should remind you of a series we've looked at already. That looks like a geometric series. Okay, this quantity here, this L quantity was referred to as R when we looked at the geometric series. But the geometric series is one where each term is given as exactly R times the previous term. Okay, so each new term you get by multiplying the previous term by R. Well, if the ratio test, if you're looking at a general series and the limit of consecutive terms of the series has a limit L, then what it's saying is approximately this series is behaving like a geometric series. Geometric series with common ratio L. Okay, when we were discussing geometric series before, we referred to that common ratio as R, but here it is with L playing the role. And so the conclusions, because you have this, our series is acting approximately or very closely like a geometric series, the main idea behind the proof is that the convergence status will be the same. So in the geometric series test, we found that these series converged. A geometric series converges if the common ratio is strictly less than 1, but it diverges if the common ratio is bigger than 1. So if the common ratio is bigger than 1, it means the terms are going to grow each time. Each time you get a new term in the series by multiplying by something which is bigger than 1. So that causes the thing to grow and the thing to diverge. When the common ratio is strictly less than 1, it means your series are shrinking, because each new term is this multiple of the previous term, but the multiple you're using is less than 1, so the terms are going to be decreasing by at this fixed rate, and so that's going to lead to a convergent behavior. Okay. So in this case, where this limit L exists, this series, the sum of AM, will converge or diverge like the geometric series. The geometric series with common ratio L, i.e. respectively, when L is strictly less than 1, it'll converge, and when L is strictly greater than 1, it'll diverge. Okay, as is stated precisely there in the statement of the test. However, you know, this borderline case of having this limit L being equal to 1, well, there you don't, it's hard to reach conclusion, because you're saying that the terms of your series are approximately, well, the terms of the series are going to be approximately the same as, each term will be approximately the same as the one that came before it. But it's quite subtle. It's, you know, if it's actually slightly smaller than it, that'll lead to a convergent series. But if it's slightly bigger than the one that came before it, that will lead to a divergent one. Okay. So because that quantity L equals 1 is on the borderline between convergence or divergence, you can't be sure which side of that fine borderline that the situation is falling. Okay. Now we'll see lots of examples of how we use this test in practice in a moment. Is there any questions about it? Just about the presentation of it there, or that discussion? Okay. So the way to think about it, the way to think about the ratio test is you're examining a series, and if you can show that this limit L exists, then what it's saying is that the series you're examining is going to behave similar to, or it's going to behave like the geometric series with that common ratio. Behave like, meaning it'll converge if the geometric series converges, and diverge if the geometric series diverges. Okay, our last, the last test is kind of similar. It still relies on, still kind of the idea of geometric series behind it. So this is the root test. And we can use this one where, well, it's pretty, in terms of the kind of problems, example problems you can solve with it, it's fairly limited. But just to ones where if you ever recognize, so it's applicable when the term AM looks like an mth power of something. An mth power of some simpler quantity. Well, if AM is like an mth power of some other quantity, and so if you take the mth root of it, so if you raise it to the power 1 over m, so raising to the power 1 over m, remember, is the inverse operation of raising to the mth power. So this quantity then will be simpler. That quantity will be simpler, and so we can analyze the behavior of this simpler quantity, and if we can do that successfully, we can deduce the convergent, divergent behavior of the original series. So let's look at the statement of the test. Again, you're finding a limit of a sequence and then drawing the conclusions based on that. So the root test says that if you take the mth root of AM, if you can show that that sequence converges to a fixed limit L, then you can draw the conclusions in the same way as we drew them before. If that limit L is strictly less than 1, you've got a convergent series. And if it's strictly bigger than 1, then you've got a divergent series. And again, we have this borderline case of where the limit L is exactly 1. And there you don't get any new information about the convergence, the divergence. It's on the borderline, and it could be falling either side of the borderline. You don't know. You need other methods to examine that. But again, the main idea, so the reason behind the proof, is again the known behavior of geometric series. Because if the limit of AM to the power 1 over m is equal to L, then eventually, or if you wait around long enough, for this sequence to get as close as you want to L, you wait around long enough for it to get very close to L, eventually AM is approximately L to the power m. So that's saying that AM is approximately a geometric term. It's approximately this quantity L raised to the power m. So this thing is a geometric term. And so the series, the sum of AM, will behave like, or what we mean by that is converge, diverge, like the geometric series, the sum of L to the power n. We know about the convergence of this thing, that it converges if this quantity L is strictly less than 1, but if the quantity is 1 or bigger, it diverges. But the borderline case, L equals 1, we can't say anything definite about, okay? Because, you know, it's only this approximate nature. So if the L is just any amount strictly less than 1, then the series, the sum of AM, will be acting like, or it will be approximately like that geometric series in terms of whether it converges or diverges. And if it's any way greater than 1, it'll be like a divergent geometric series. But if this L quantity is coming out at exactly 1, we can't say which side of that dividing line the series AM is falling. So what's that? That was the root test. Okay. So that's kind of a theoretical discussion of them. I'm just giving some motivating arguments for the proof of them, some explanations of them, some ways to think about them. So what we should now do is look at several examples to see them in action and to see how you use them to test a given series and how to draw the conclusions from them. Okay. So we'll look at that now. Finish with that page. Yeah. Okay, so let's look at some examples. So first example we'll look at is this one. We'll examine the series. So we'll go sum from n equals 1 to infinity. We'll look at the term 2 to the power 2n over n to the power n. Okay, so we'll look at the series. Now, very often, if you're just somebody shoves a series in front of you and doesn't give you any further guidance, then you need to kind of go through the list of convergence tests you have, as if it's like a toolbox, and select the right tool. Okay. It may be a process of trial and error. You might try various tests on it. It may be that more than one convergence test will work on it and will tell you what this series is doing. Maybe that none of them will, and maybe that it, you know, this is not in a correct form or is too complicated for any of those tests to work on. But what is it about this one? Well, you see, you can see the index variable n is in the power position. So there's some nth powers here of something simpler. So maybe this is the root test, okay? So the observation is we see nth powers taking place. We see nth powers taking place, so we'll try the root test. Okay, that's the observation that's leading me to the root test. So, well, first of all, we'll just rewrite it so that we can see the nth power explicitly, because this series is equal to, if it is convergent, if it does have if it does has a limit, then we can re-express the term like that. Okay, so it's that nth power taking place in the numerator and the denominator, so you can take it outside and apply it to the simpler fraction as a whole. So that's sum of 4 over n all raised to the power n. So we can apply the root test now to this series. So we examine now the limit as n goes to infinity of a sequence, and that sequence is our series term, which we've now expressed like this, and we take the nth root of it. So you can see now how that's going to simplify the thing we're examining. We're now looking at the limit as n goes to infinity of 4 over n. But this quantity, we know the behavior of this limit of this sequence. This is the limit 0. Okay. So our L is equal to 0 in the notation of the notation of the statement of the convergence test, which is theorem 2.10. So we can say that this series, the sum of 2 to the 2n over n to the power n, converges. Converges by the root test. Okay. So we carry out the test by examining the limit mentioned in the test, figuring out what this quantity L is, and then drawing the conclusion based on L that the test tells us we can make. Okay. Let's look at another example. Here we're going to examine this series. Well, this kind of screams out what to do with it, because you've got this -1 factor to, okay, in this case it's to the power n plus 1. Okay, so this is an alternating series. The other bit, the other factor, the 1 over the square root of n, that's a positive quantity. So this series is going to be stepping up and stepping down, stepping up and stepping down, with a step size given by 1 over root n. Okay. So the alternating series applies to this. And since the step size 1 over the square root of n, since it converges to 0 as n goes to infinity, then this series is going to be convergent. Is convergent. It doesn't tell you what the limit is. That's a whole other matter. Finding whether or not you can determine what the exact limit is, or is another matter entirely. But the test does tell you that it converges. Of course, you can, if you want to get an approximate value for the limit, you can just evaluate a large partial sum. Okay, just take in the first 1,000 terms, and that will give you a pretty good estimate of the, or would it? Well, the term here is 1 over the square root of n, so actually the term is converging to 0 a bit slowly, perhaps. So even if you take the first 1,000 terms, well, what's the square root of 1,000? Well, it is whatever it is. If you take the first 100 terms, then the step size is still a 1/10. So, it's still stepping up and down by a relatively large amount. So maybe you'd have to take a lot of these terms to get a relatively good approximation of the limit. But the test tells us that it is converging. Now notice with this one, if you don't have the alternating plus and minus sign, so if you just look at the sum of all these terms 1 over root n, this series diverges. This is an example of a hyperharmonic series. So this is the hyperharmonic series, the sum of 1 over n to the power half. Okay, and we discussed before that the sum of 1 over n to the power p, it converges if that exponent p in the denominator is strictly bigger than 1. But if it's less than or equal to 1, then you've got a divergent series. So just adding up the absolute value of all these step sizes produces a divergent series, but if you take them in an alternating fashion, it will give a convergent series. Now then, so okay, Any questions about that or clarification you'd like on that? Okay, so we haven't seen any examples of the ratio test yet, so let's be on the lookout for that. Well, it's coming up next. So let's look at this test. Or this series, the sum of n over 3 to the power n minus 1. Passes the general term test in that these terms, n over 3 to the power n minus 1, we can probably, I think we can fairly easily appreciate that those terms, the terms as a sequence of terms are going to be converging to 0. If you think of a large value of n is 10, 10 over 3 to the power 9, well, it's going to be extremely small. 100 over 3 to the power 99, it's going to be microscopic quantity. So the terms are certainly shrinking and converging to 0. So this series, it's not obviously divergent. Maybe it could converge. But the general term test, remember, never tells you that something definitely converges. The outcome you get from the general term test is that perhaps the series, you might be able to say that the series diverges for definite. But because these terms are converging to 0, it's kind of maybe it converges. Well, we also recognize that because of the n is in the exponent position, because you've got this simple factor n here, if you form a ratio of consecutive terms, that should be fairly straightforward to handle, because you'll have one power over another power, so you might get cancellation there, and you'll have an n over n plus 1, and that should be fairly easy to understand. Okay. So this looks suitable for the ratio test, you can say. So we'll try it. We'll look at the limit as m goes to infinity of a to the m plus 1 over a to the power m. So the conventional way to do the ratio test is to take a general term in the series and divide it by the previous one. So am plus 1 over am, or you could say am over am minus 1. But it's a general term divided by the one that came before it. So what would this look like? This would be the limit as m goes to infinity. So am plus 1 will be m plus 1 over 3 to the power m. That's am plus 1. And then we need to divide it by am. Well, dividing it by am will be the same as multiplying it by its reciprocal. So we're taking the limit of that. M plus 1 over 3 to the power m multiplied by 3 to the power m minus 1 over m. Well, there's lots of cancellation you can do here and maybe reorganize it in a nice way. All the 3's are going to cancel except for 1, because there's one extra factor of 3 in the denominator, isn't there? There's m minus 1 3's up here, but there's m 3's down here. So you're going to get a third factor there. And then you've got m plus 1 over m. Or a nice way to rewrite that is simply 1 plus 1 over m. If you just expand the fraction, it'd be m over m plus 1 over m, so it'd be 1 plus 1 over m. Now, how is that behaving as m goes to infinity? Well, these are fixed constant bits, a third and 1, and this bit, 1 over m, that's converging to 0. Yeah. So we can use our algebra of sequences result to say that the limit of this is a third. That's a third, since 1 over m is converging to 0 as m goes to infinity, and that's by the algebra of limits theorem. You all brought your raincoats today? So you see how it works. You perhaps recognize some structure in the series term which makes it look like you'll get nice cancellation when you look at the ratio of consecutive terms. Oh, I haven't got the ratio test up there. I should put it back up. So when you look at this ratio, am plus 1 over am, simplify it as much as you can, and then if you can, determine its limit. So the limit we get here is a third. So drawing the conclusion, it's because that is strictly less than 1. So L equals a third in the notation here of the test. So we found L to be a third, and so because that's strictly less than 1, then so this converges since L is strictly less than 1. Yeah, does that make sense? Let's finish with another example. Here we're going to examine this series. Now we're going to look at n factorial over 3 to the power n. Well, you see exponents and you see factorials. If you form a ratio of one factorial over a closely related one and one exponent, one power over a closely related power, then they will cancel nicely. They should simplify. Okay. So factorials, powers, these things mean try the ratio test. May not work, may not give you a conclusion, but it's certainly a good indication that it will. So we're going to look at the limit as m goes to infinity of am plus 1 over am, as before. So am plus 1 will be n plus 1 factorial over, sorry, m, I'm using m here, m plus 1 factorial over 3 to the power m plus 1. And dividing it by am will be to multiply it by 3 to the power m over m factorial. Well, when that you mush all that together, the factorials cancel to leave you with the factor of m plus 1 in the numerator position. So there's an extra factor m plus 1 up here. But all of these, all the factors involved in m factorial cancel with their partners in m plus 1 factorial. And the 3's all cancel except to leave a third here in this position. So this is the constant, a third can come out. You're looking at a third times the limit of m plus 1. Well, this is a divergent sequence, isn't it? Just the limit of m as m goes to infinity. So that's divergent. Divergent sequence. So in the language of the statement of the theorem, we don't have a limit L which is strictly less than 1. Okay. So we don't have this limit L as being strictly less than 1. And so this series, the sum of n factorial over 3 to the power n, this is divergent by the ratio test. Okay, so we might say a bit more about this, and we're going to, when I see you tomorrow afternoon, and there's an important application of the ratio test to the concept of power series or Taylor series, which are an important idea in mathematics. And in the tutorial exercises, you'll find examples of series which are decidable using these tests. And also check the Schaum's Outline of Calculus book. That's a very good book as well. It's got lots of solved problems, lots of practice problems, and it's got some good sections on these tests. Okay. So I'll see you tomorrow afternoon.